Good afternoon, everybody. My name is Alberto Ardit. I'm from the University of Canterbury in New Zealand, and today I'll be presenting you a work called Heat Flux Estimation from empty models and temperature logs, with applications to the Wairakei Geothermal Field in New Zealand. Today I'm representing the University of Auckland and the University of Canterbury in New Zealand. So, high-temperature geothermal fields usually present three major components: a heat source, which could be a shallow magma or a cooling pluton, overlaid by a reservoir, which are basically hot fluids trapped in a permeable rock, overlaid by a clay cap, which is an impermeable rock formed through hydrothermal alteration that prevents the hot fluids from the reservoirs to reach the surface. In this presentation, we will be focusing on the clay cap, and we will be trying to infer the boundaries of that clay cap from direct and indirect observations. So, the clay cap in geothermal exploration can be observed from, as I said, by direct or indirect measurements. In terms of the direct ones, we usually use well logs, where we can infer the presence of the clay cap from methylene blue titration technique, which is an indicator of the clay content in the well, and also using temperature profiles. And because the shape of the temperature profile can give you inferences of the type of heat transfers that is being conducted in that particular section. Also, we can infer the presence of the clay cap from geophysics, using geophysics from the surface, and in particular from all of the geophysical methods, the electromagnetic methods has been proved to be the most useful one, and among them, magnetotellurics is the one that have proved more valuable when capturing both the top and the bottom boundaries of the clay cap. The core of our research to infer properties of the clay cap relies on empty methylene blue inversion that we develop to quantify the uncertainty when capturing from the empty inversions the top and the bottom boundaries of the conductor that is reflective of the clay cap. So the whole thing goes like this. If you go to the figure, the first figure, the figure 1, is the place where we measure empty signals and from the surface, and we extract methylene blue inferences in the locations of in the wells profiles, as I'm showing here close to this empty station called C. Then we use a 1D Bayesian inversion to invert using a 3-layer models, looking to capture the top and the bottom boundaries of the conductor. And in this step is where we use the methylene blue logs information to try to constrain the non-uniqueness inherent in the empty inferences. So for each of the station, we invert for a 3-layer model constrained by the methylene blue data, right? And then if we move to the last place, here in C is where we just kind of interpolate our uncertain inferences for the top and the bottom boundaries of the clay cap in each station to construct pseudo profiles of the most probable locations of the top and the bottom boundaries of the conductor. And what I'm trying to reflect here is that in the places that you are close to a methylene blue well, like here, the station C, the inferences will be, the non-uniqueness will be restricted even more, so the uncertainty will reduce significantly using this methylene blue informations for the empty inversion. Our empty methylene blue inversion we formulate using the base equation where we invert using a 3-layer model that contains 5 parameters. 3 parameters for the resistivities for the first, the second, and the half phase for the first, second layers and the half phase, and 2 parameters for thicknesses, the thickness of the first layer and the second layer, where the second one is the one that we are trying to capture the clay cap. We quantify posterior PDF over the thicknesses and the resistivities of these layers, given the MT observations. And we quantify this posterior using as a likelihood function, where is the place that would fit the MT data or the MT observations in the surface. And we constrain that likelihood using prior distributions on the layer resistivity. In this case, we just use like uniform prior that set a range for the plausible resistivities for the particular layer, and we also impose a prior on the thicknesses of the first and the second layer based on the methylene blue data. So we construct those priors using observations in the well, so it could be considered like an empirical prior, and we use the methylene blue to constrain the thicknesses, so it could also be thought as an structural prior. So this is kind of the key part of this inversion, that we are constraining prior distributions for the thicknesses of the first and the second layer using the methylene blue data that we observe in the wells. Now, one of the essential parts to understanding our work is how do we go from methylene blue data to methylene blue priors. What I'm showing here in the first panel is methylene blue data from a well in the Wairakei-Geothermal Field. The data is shown by the red asterisk. And we, in a Bayesian framework, we invert this methylene blue data using square functions. The square functions are the ones showing in cyan here. So the parameters that define that square functions are the one for the top of the square and the bottom of the square, and we assume those as indicatives or the most probable location for the top and the bottom boundaries of the clay cap. So once we have estimated using a Bayesian framework the values or the distribution for those parameters, which are the ones that I'm showing in the histograms at the bottom, we use those distributions of the most probable location given the methylene blue data of the top and the bottom of the clay cap. And those are the ones that we then use in our Bayesian framework as structural prior or prior information based on the methylene blue data. So once we have built the methylene blue prior, we use those prior to invert the empty data in the empty station locations. So what I'm showing in the plots in the right are the inversion of an empty station in the Wairakei-Geothermal Field with the methylene blue prior, and on the left using the same station but inverting without the methylene blue prior. In the first two plots, what you can see is the place where we feed the data. So those blue lines are showing our estimations from the Bayesian inversion. And so far, you can notice any significant difference by using the methylene blue prior or without the methylene blue prior. But when you go to the models that are the one in the second rows, those are the 3-layer models that generate the surface response to fit the data in the first two plots. When you go to them, if you focus first on the one without the methylene blue prior, you can see that the distribution for the parameter that define the bottom of the second layer, which is a reflection of the bottom of the conductor, the uncertainty that you get without the methylene blue prior is much higher than the one when you use the methylene blue prior, which is the second plot, the second row right plot, right? So you can see from there how the uncertainty on the estimation of the bottom of the conductor is highly reduced when you use the methylene blue prior. That is reflected too, or we reflected in the marginal posterior, the histograms that are of the distribution of the parameters that we are showing on the bottom, where in the last one, which is the one that define set 2, which is the one that define the bottom of the conductor, the distribution between when you use the methylene blue prior is highly reduced compared to when you don't use the methylene blue prior. So this is a great example of how this inversion helps to quantify and reduce the uncertainty when capturing the boundaries of the conductor, in particularly the bottom of the conductor. What I'm showing here is a synthetic example where we try to estimate the clay cap boundaries using our method and compare it to inversion using 2D MoD-M. So in the first plot we're showing a true resistivity distribution. In the second is the estimate resistivity distribution from the MoD-M inversion. The third one in C is the one using our method but without the methylene blue prior, where this is an example where we try to capture the top and the bottom boundaries with uncertainty. And in the last plot in D is the empty inversion using our method but with the methylene blue prior. And in that one we try to quantify which one performs better. From that analysis we conclude that our method using the methylene blue prior is the one that captures better, in particular the bottom of the conductor. And what I'm showing here is a real inversion of a profile in the Wairakei geothermal field, where we capture the uncertain top and bottom boundaries of the clay cap and compare it to temperatures in wells and also to lithology. From that analysis, we get good agreement with well lithologies and logs, and it also helps us to characterize the nature of the different clays that we observe in the field. So this is an example of how our inversion looks like. The red and the blue and the orange envelopes are showing our uncertain estimation of the most probable location of the top and the bottom of the conductor, inferred by the methylene blue data and the empty data. A following exercise that we develop once we have the inference for the top and the bottom boundaries of the clay cap was mapping the temperature logs in those boundaries that we have inferred for the clay cap. From there, we can sample which are the temperatures observed at the top of the conductor and in the bottom of the conductor. And that is being shown in the plots, where if you go to the bottom ones are the distribution of the observed temperatures at the top of the clay cap and the bottom of the clay cap, that help us to quantify which is the temperature formation range for the clays that forms in the clay cap. Then, once we have mapped the temperatures in the location of the clay cap, we develop a formulation to quantify the conductive and advective heat transfer that is occurring through the clay cap, based on this heat transfer equation that is being shown here. So in this step, we develop a formulation where we fit the temperature profiles inside of the inferred clay cap to quantify the contribution from conduction and advective heat transfer, and in that way help us to quantify the total heat flux that is being passing through the clay cap. The result of that formulation or that development is showing here, where we quantify the temperature gradients through the clay cap, but also the heat flux as a contribution for conduction and convective and advection heat transfer through the clay cap, that we map it through the field, and that help us also to quantify the total heat flux that is passing through the clay cap for the Wairakei geothermal field, that we quantify to be 380 megawatts, which is kind of a minimum range, a minimum limit for the total heat flux in the system. The series of methodology that I have introduced you here today can be reviewed in the following papers that I give you in the slides, where the first one is the place where we show all of the formulation for the empty and methylene blue inversion, and the second one is the one that we explain how the heat flux calculation works, and the results for the Wairakei geothermal field. And finally, thank you for your attention, and I hope you have enjoyed. Bye.